Hello everyone, welcome back to Science Icons once again. So today we have come up with a new video on a separate topic, and this is going to be the part 2 of whatever I have started in my previous one of the chapter 4, as you can already see here. Initially we were discussing about movement of forces, force, different types of motion, the rotational motion, the translational motion, how do we represent them, the couple of moments and everything. Today we are going to deal with completely different topic, that is center of gravity and centripetal as well as centrifugal forces. They are very small topics, but it's important for boards. Okay. First of all, we have to know one thing, that the first chapter of class 10 is divided into 3 portions. The first portion deals with moment of force, couple, the principle of equilibrium, which is the most important thing for solving numericals on the chapter. After that, we have part 2 that deals with center of gravity, and part 3 we have that deals exactly with centripetal and centrifugal forces. Fine? I'm going to tell only those things which are actually essential along with the keywords for the definitions alone. First of all, let me read out one thing from the book for center of gravity. Mark the words. Okay. Earth attracts every particle towards its center by the force of gravity acting on the particle. Right? Like if I'm standing on 5th floor, I am being attracted by the earth. So each and every particle around me is getting attracted by the force of gravity. Now, this force which is acting on me, if I speak from my point of view, it's my weight. It's a basic, very simple thing. Let me repeat once again. If I'm standing on 5th floor and the force of gravity is attracting me, it's trying to pull me down towards the center of the earth, then from my perspective, from my point of view, it is going to be my weight. Mass does not change, but weight changes. If you go to the pole, you will find some other weight. If you go to the equator, you will find some other weight. That's why weight is changing, because according to the places, the force with which Earth attract a particular thing varies. If you measure your weight standing on the 1st floor, and if you measure your weight standing on the 10th floor, mark one thing, there is going to be a change in the magnitude of the weight. Never it will be same. If you measure your mass, it will be always be constant. Even if you go on moon or any other planet, Jupiter, everywhere your mass will be same. But weight will change everywhere. On your earth, weight is something. If you go on moon, your weight will be something. Right? Now, the weight W, the weight of a body, any body, the weight of that body. The weight is considered to act at a point G such that the algebraic sum of moments due to weights of each particle about the point G is 0. That means, suppose I have taken up any irregular body. I've taken up any irregular body. We have so many points on the body, we have so many particles, but all the weights are acting down. All the weights are acting down. Since the particles are very small, we can assume that the weights which are acting here are parallel to each other. Now, what we are assuming is there is one common point. There is one common point from where the weight is acting. Let this point be G, and let this weight be W1, W2, let this be W3, and let this be W4, let this be W5. So G is such a point which is the sum of all the points of weight. It goes on like this, whatever is the point. So G is such a point. My G is such a point where all the weights are getting added. Right? So this we have to know. That's why see what I have read out just now. W, the W which is the weight here, representing the weight of different particle, is actually considered to act at a particular point which we have assumed here as G. Fine. Now, to make this point center of gravity, the algebraic sum, note the point which I am calling out from the book. The algebraic sum of moments due to weights which are acting of each particle about the point G should be 0. That means If I mark this point as G and if I try to balance this body, then all the weights which are acting is somewhat bringing moment in it. The algebraic sum of all these moments about this point should be 0. If the algebraic sum of all the points at this point is 0, that means the moment of force on both the sides are getting balanced. If I balance this particular body on the point G, the body is going to be in equilibrium. It will never show clockwise rotation nor it will show anti-clockwise rotation. It will be balanced, it will be in a state of equilibrium whenever the body is not or balanced at point G. This particular point can be called as center of gravity. So center of gravity is such a point. I'm just reading out the definition. The center of gravity of a body is the point about which, mark the keyword, the algebraic sum of moments of all the weights of all the particles constituting the body is 0. The full point has to be written. Without this, no marks. The entire weight of the body can be considered to act at this point, howsoever the body is placed. In whichever way I place this body, the body indeed is going to be balanced at this particular point. That means by balancing the body in any position at this body, the body will obviously be in equilibrium. Right? Now the position of center of gravity of a body depends on the mass of a given mass, depends on its shape, that is distribution of mass. It changes if it is deformed. For this body it is something else. If I take body like this, it will be something else. Body like this, it will be something else. Okay. Now it is not necessary that center of gravity should always be within the body. I'll tell you why. I'll give you examples. By the concept of center of gravity, a body of weight W can be considered as a point particle of the weight W acting at the center of gravity. Fine. The third point was not so important because it's a bit conceptual, which I've already explained. Now let us see few examples. Let us see few examples. Now, the first thing is rod, a uniform rod. This is my rod. Then the exact midpoint, suppose this is 100 centimeter, then the exact 50 centimeter mark, if I balance it here, it is going to be balanced. If I try to balance or bring the body in equilibrium by placing the fulcrum at 50 centimeter mark, if it is a 100 centimeter rod, then it will be balanced. Okay? So midpoint of the rod. So if it is a rod, then it is going to be at the midpoint of the rod. Next is circular disc. What in case of a circular disc? Suppose I have a circular disc like this. The geometric center is going to be the circular disc. And see, here comes the example. The center of gravity is not lying on the body, it is outside. But somehow, by using strings and all, if we balance the body at this point, the body is going to be balanced. Okay? After this, we have solid or hollow sphere. Solid or hollow sphere. For this, the geometric center of the sphere is going to be your center of gravity. So the geometric center, I cannot draw this 3D diagram. So geometric center of the sphere is going to be the center of gravity for this particular body. After this comes solid cone and hollow cone. Now this I am going to tell at last. Okay, because numericals come from here, I need to tell few things about this. At first let me cover the last three things. Number 4 is circular ring. What about a circular ring? The center of the ring. Then comes number 5. Number 5 is triangular, laminar, or scalene triangle. So I'm just writing triangle and explaining it. So for triangle, the point of intersection of the median is the center of gravity. That means if I draw a scalene triangle, the point of intersection of the medians, I'm just roughly drawing it. Point of intersection of the medians, okay? Point of intersection of the median is the center of gravity. Next comes parallelogram. Parallelogram. The short form is written like this. For rectangular lamina, so for rectangle, and for square or rhombus. And for rhombus. The point of intersection of the diagonal, that means suppose I am drawing rectangle only, the point of intersection of the diagonal. Point of intersection of diagonal. What if it is a parallelogram? Nothing is going to change, even if it is a parallelogram. Point of intersection of the diagonals. Now what about solid cone and hollow cone? Now I did not say much about this because I have nothing to explain. I have just blankly written what is there in the book. Okay, I have just copied it from the book because nothing is to be told here. No concept is to be applied. Simply if question comes from here, hardly MCQ based questions come, you will have to just blankly know the points and choose the correct option. That's it. Nothing is to be done. Numericals come from the portion which I am going to tell right now. Now we have two things, hollow cone and solid cone. These are the two things, number 1, number 2. Hollow cone and solid cone, these are the two things that we have to know. At first let us know what is hollow cone and we have to know what is solid cone. Let me draw a cone for this. I'm just roughly drawing it. So let this be a hollow cone, that means we just have the body, the outline, there is nothing inside, like a birthday cap. Okay, that is a hollow cone. And if it is solid cone, that means the inside is fully filled with mass. Okay, it's not hollow, it's solid. Now, for all other body, rather for all other shapes, the center of gravity comes using the formula that I have told you, there is no change. But in case of a cone, we have two variations. One is hollow, another is solid. With this variation, with change in the mass, the center of gravity also changes. Because I have already said one point, center of gravity depends on the shape of the body, that is distribution of mass. If the hollow cone is becoming solid, then distribution of mass automatically changes. That's why the formula through which or using which we can find out center of gravity changes. Fine? Now what if it is a solid cone? Now this is the height, this is the radius, this is because this is a circle, circular base, this is the radius, this is the height. And this particular thing is known as slant height. This we denote by the letter L. This is your height, this is your radius. Same goes for this is your height. Now we need not to know what is slant height, we do have one formula also. But we are not going to learn about this because our work is with height. We will neither work with slant height nor we will work with the radius. We just need to know the height. Fine? Now if it is a solid cone, then the center of gravity lies at the point which is h by 4 from the base. I'm just reading out, at a height h by 4 from the base on its axis. if h is height of the cone. So if h is my height of the cone, then h by 4 from the base is going to be the center of point of CG. And at that point of time, or at that place, if it is a hollow cone, then the formula becomes 3, h by 3 from the base. Same concept, here it is 4, here it is 3. Now you will ask me why? Because when we talk about solid cone, more mass is concentrated at the bottom, more mass. Because see, the area, or if you no need to look about there, look into the area, just think about the volume. The volume is more at the bottom, so there is more mass, right? It is, the shape is like this, so automatically the bottom portion carries more mass. So the center of gravity comes down. In that place, when we talk about hollow cone, then the bottom portion is completely empty, but the top portion, automatically the mass there increases. Increases in the sense more mass is concentrated on the top portion. Okay, you cannot say that the mass is getting increased. No, mass is not getting increased, but more mass is present on the top portion. When we compare, or when we see with respect to the mass which is present at the bottom. That's why the center of gravity, the CG, the point of CG goes up. That's why it's h by 3. This is the simple logic. Now, this was all. Nothing is to be done from here. Two things we have to do. Two things. And this is important for examinations as well, because questions come from here. For stable equilibrium, okay, if we want to bring a stable equilibrium in our body, what are the two things that we need to remember? So just see, for stable equilibrium, I'm using the book's word, the words I'm writing from the book so that you can understand. Its center of gravity must be as low as possible. So first point is the CG. CG is the abbreviated form of center of gravity. The CG must be as low as possible and it must be above the base. It here refers to point of CG. It must be above the base. I'm just breaking the second point into another point. Okay, it could have been written in one point only, but I'm breaking it down for simplicity. And near the geometric center of the body, it must be near the geometric center . So we have to know these 3 points. Fine. This was all about center of gravity. Now we come to centripetal and centrifugal forces. Now the chapter, the exercise is termed as uniform circular motion. Now when a particle moves with a constant speed in a circular motion, its motion is known as uniform circular motion. Okay, that means we have a circular body like this. And the body is, with a particular speed, the body is rotating on this particular path. Then we call it uniform circular motion. Fine. Now, at any point, we have to just know 2 things. I will not tell any extra. Suppose the body is moving in this direction. V represents velocity. At any point, velocity is towards the tangent, because what we know, tangent is a line that just touches a circle at a particular point and goes away and never meets. That is tangent. So see, at this particular point, this is the tangent. So velocity is tangential, that is towards the tangent. Fine. So velocity is only same at a particular point, that is towards the tangent. The moment from this point it comes to this point, the body, I repeat once again, the moment it comes from this point to this point, the velocity changes, because velocity is a vector quantity. Vector quantity needs both magnitude as well as direction. So if there is any change in direction, the velocity automatically changes. Speed remains constant, but velocity does not remain constant. It changes due to the change in direction. So at a particular point, tangentially it is in the same direction. Because it is towards the tangent, that's why the direction is same. So we can say at a particular point along the tangent the velocity is same. But as the body moves, leaves that particular point, direction changes, velocity changes. And we have to know one more thing. At any point, the direction of motion is along the tangent. The direction of motion, velocity, same thing, of the circular path. Now, this is a non-uniform, or rather, let me say, it's an accelerated motion, because acceleration is when do we say that the motion is accelerated? When there is a continuous change in velocity. Here, the velocity is continuously changing, right? So we can say it's an accelerated motion, and the acceleration takes place towards the center. It takes place towards the radially inwards towards the center. We have to know these two things. Velocity is towards the tangent. Velocity is towards the tangent, or we can also say tangential. And A, that is acceleration, is towards the, or we can also say in this way, radially towards the, radially inwards towards the center. Okay, radially inwards towards the center. Fine. Achha. After this, the velocity of the particle is variable, or the circular motion is an accelerated motion even though the speed of the particle is uniform. Now, difference between uniform circular motion and uniform linear motion. In uniform linear motion, the speed and velocity both are constant, but acceleration is zero, because in a linear motion, the velocity does not change, it remains constant. But in uniform circular motion, the velocity is variable, although the speed is uniform, and therefore it is an accelerated motion. That's it. Now we come to centripetal and centrifugal forces. Now, to put up the body in this particular uniform circular motion, a force is required, right? The force is known as centripetal force. I'm going a bit fast because these concepts are very easy, and I've already covered a part of it in my, I guess, part 1 of this. Okay. So, centripetal force is acting towards the center, right? So, this is the force which is driving the body to continue in that particular uniform circular motion. Okay, so if I read the definition from here, centripetal force is the force acting on the body moving in a circular path in a direction towards the center of the circular path, right? Now, the direction of the force and also the acceleration changes at each point of the circular path, but the magnitude remains same. That's because when the body is here, or if I draw here once again, this is the center. When the body is here, force acts in this direction. When the body comes here, force acts in this direction. So the direction changes. The direction changes, but the magnitude remains same. Now here comes a little bit of confusion. What is the work done? Okay, it is not a part of this chapter, it is a part of the next chapter, but I am telling you here. Work done, we know, is equal to Fs cos theta. This is the formula I have already covered in one of my previous video of work, power and energy. So work done is equal to Fs cos theta, where F is my force, S is my displacement, cos theta is the angle, right? And W represents the work done. Now we know at any point, this is my velocity, this is the direction of my velocity, and this is the force. Always we can see between the angle between the force and the displacement, that is, the displacement is taking place in this direction, is always 90. Even if you see here, see, it's a right angle that is formed. Right angle is 90 degrees. So if I put in the formula, whatever be the value of Fns, we need not to get, puzzled with the values of Fns. Let Fns be anything. We know theta is equal to 90. We know this much. We will just put cos theta 90 in place of theta, so it becomes cos 90. And we know cos 90 is equal to 0. Cos 90 is equal to 0. So W is equal to Fs into 0. So W becomes 0. So the work done here is actually 0. Fine. So after this, the last thing for today is the centrifugal force. Now what is my centrifugal force? Now a force assumed by an observer moving with the body to be acting on the body in a direction away from the center of the circular path. Now, if you are an observer in the motion, you will find that a force is acting away from the circular motion. It is acting away from the circular motion, and that particular force is known as centrifugal force. Okay, this is known as the centrifugal force. So it is acting in a direction away from the center. Okay, so if you are being asked what is the direction of centrifugal force, you have to say it is acting away from the center. That is, it is trying to oppose centripetal force. So centrifugal force, centripetal force are opposite. Okay. Now you can say that centripetal force is the force of action and centrifugal force is the force of reaction. You can say, but actually it is wrong, because centripetal force is acting on the body who is rotating or who is in that uniform circular motion, and centrifugal force is also acting on the same body. But according to Newton's third law, we know action and reaction never gets applied on the same body. It always gets applied on different bodies, two different bodies. But here, both centripetal as well as centrifugal are getting applied on the same body. That's why it's not at all action reaction. So we cannot say that it is obeying Newton's third law of motion. Fine. Henceforth, it is not a real force. It is also known as fictitious force or virtual force. But yes, it acts. Okay, it is not a real force. It is a fictitious or virtual force, but still it acts on the body. Fine. Now a person, okay, the person who is actually experiencing that particular motion will observe two things. First is the tension T of the string towards the center of merry-go-round. That means he will find that a tension is getting acted. A tension is getting acted here. That is the force which is driving or which is keeping the body in motion. The tensional force. Okay. If someone is in a merry-go-round, for example, if someone is in a merry-go-round, he will find that tensional force is getting acted on the string, okay, towards the center. And the centrifugal force is acting away from the center. So that centripetal force is the tensional force there, right? It is acting towards the center, and centrifugal force is acting away from the center. That's it. Henceforth, if we conclude, centrifugal force is not real force, it's a fictitious force. The only real force involved here is the force of tension, which is the centripetal one. Henceforth, we can also call or describe centrifugal force as fictitious or virtual force. Okay, so this was a small basic thing about part 2 and part 3. Okay, and with this I have completed with force. We'll move or come in my next video with the next interesting chapter. So hope you have liked my video. If you like my video, please like, share and subscribe it. Also press the bell icon. Wait for my next video. Stay tuned. For that only I have told you to press the bell icon and be ready to to go on the journey of more interesting and hard, of course, as well as intellectual and tougher concepts. Okay, thank you.